take out your highlighters again, and there's a special case of the remainder theorem called the factor theorem. If your remainder is 0, when you write your division statement, it looks like it factors out perfectly, and that makes whatever you're dividing by a factor. So if our remainder is 0, then we have a factor. So the factor theorem says if you plug in a value and you get 0, if P of A is 0, that means that x minus a is a factor. And one of the things that we're leading towards in this unit is factoring things that you haven't been able to factor before. How do I factor an x cubed equation when there's lots of stuff? How does that work? What does that look like? So if we look at example 2, they give us a bunch of options. X plus 1, x minus 3, x minus 4, and x plus 4. And they say which one of these are factors. So when looking at these, based on the numbers, I would probably use the remainder theorem or the factor theorem for the first one, because I'm going to let P of x equal this whole thing. And if I want to find the remainder when I'm dividing by x plus 1, I can plug -1 into that equation. And -1 is really easy to calculate powers of. So I'll just write it in: squared plus 5 times the -1 plus 12. -1 cubed will be -1. This will be positive times the -6, -6, minus 5 plus 12. And this is equal to 0. So since the remainder is 0, that makes x plus 1 is a factor. So that used the remainder theorem and the factor theorem. Basically, they're the same thing, but the fact that the remainder is 0 tells us that this works out perfectly to be a factor. Now, in part B, just change colors. In part B, if I was dividing by x minus 3, with the remainder theorem, I'd have to plug in 3. And plugging in 3, in this case, 3 cubed, it's not too hard to do, but I'll deal with some bigger numbers. So sometimes dealing with those bigger numbers, I find in those situations I like to go to synthetic division. So for synthetic division, I'd have 1, -6, 5, 12. I'd put a positive 3 out here, so 1, multiply, add, multiply, add, multiply, add. And that last value is our remainder. So we can tell on this one that x minus 3 is also a factor. Again, C and D, both larger values. So for C, we're dividing by x minus 4. Is it x minus 4 in C or x plus 4 in C? X minus 4 in C, so there'd be a positive 4 out here. 1, -6, 5, 12. Bring down the 1, multiply, add, multiply, add, multiply, add. And again, we get a remainder of 0. That tells us that x minus 4 is a factor. So what would it look like if something wasn't a factor? Well, in the last one here, again, I'll use synthetic division. This time it would be a -4 if you're dividing by x plus 4. Bring down the 1, multiply, add, multiply, add. Here we do get into some bigger numbers. We get a remainder of -168. That tells us that x plus 4 is not a factor. Now, one of the things that we're going to do after this is factor things completely. And in this case, we found 3 factors. We could write those 3 factors, and it's going to make sense that that works out perfectly. But what I want to show you, and I'm going to take part C as the example. Okay? I'm going to write the division statement from part C. So we have our original function p of x, which I'm not going to write the whole thing out, but the division statement from part C tells us that when I divide it by x minus 4, so my divisor is x minus 4, my quotient, the answer that I get, is x squared minus 2x minus 3. That's my quotient. And there's no remainder, so this is what it would be, because it would be plus 0 at the end, which you don't need to write. And if I wanted to factor this completely, well, this is a quadratic equation. We know how to factor those. X, it's going to be minus 3 plus 1. And now we've factored this completely. So one of the skills that we're going to learn is if we can find one factor, we can do synthetic division and write the division statement until we can factor it completely. Now, in this example, if we view the whole thing that we did here, in this example, we found x plus 1 as a factor, x minus 3 as a factor, and x minus 4 as a factor, and sure enough, all 3 of those factored to be the whole thing. Now, they gave us these numbers to try. So we just were trying the ones that were given to us, and we found 3 that worked. The question's going to be, how do we know which numbers to try? Because if you started with x plus 4, it didn't work. And if you just kept guessing randomly, there's only 3 that work, and there's an infinite amount of ones that don't work. How do we choose the right ones? Well, we use something similar to what we used when we factor regular quadratics. You notice that when you factor this regular quadratic, that to get x squared, these first ones multiply to x squared, and the minus 3, the last ones always have to multiply to minus 3. The same thing happens when you get to a bigger polynomial. This bigger polynomial that we have, the first term is an x cubed, the last term is a 12. Notice all of your first ones, x times x times x, make x cubed. All of your last ones, negative 4 times negative 3 times a positive 1, they make positive 12s. And when you're multiplying 3 like this, your first ones multiply to get your first ones, your last ones multiply to get your last ones, and all the stuff in the middle is like a whole bunch of extra outside, inside, outside. It's like something like that. We don't actually write it out, but there's a bunch of things happening on the insides. But the important thing to notice is that your first ones need to multiply to your first one again. Your last ones still multiply to your last one. Okay, for practice 10A and 12.